And welcome everyone. Thank you, Professor Karpenko, for being here this morning. Today's presentation by Professor Karpenko will be on sketch-based interfaces. I wanted to give a brief introduction to her for those of you who are not familiar with her. So Dr. Karpenko received her bachelor's degree in applied math from Moscow State University and an MS and PhD in computer science from Brown University in Rhode Island. And before joining USF's faculty, Professor Karpenko was a postdoc researcher at UC Berkeley. And I'm going to go ahead and mute our participants that are not presenting because I can hear background noise. But with that, I apologize for the brief interruption. But with that, I'll turn it over to Professor Karpenko so you can talk about sketch-based interfaces.
Thank you very much, John. Welcome, everyone. Good morning. So I'll actually talk about specific kinds of sketch-based interfaces, specific kind called interfaces for 3D modeling. So particular kind of sketch-based interfaces, because there are so many of them. So I'll just focus on those. But maybe we can start with what is actually a sketch? What do you mean by sketch? And definition of a sketch depends on the medium. So if you're talking about a drawing, then you probably mean a drawing that's sort of rough and informal. If you're talking about a sketch of a book, right, a novel, then we're talking about just description that's a bit rough, but has the essence of the story. So in both cases, and there could be other definitions of a sketch, but in all of those cases, this is something that's sort of rough, right, maybe unfinished, but something that definitely captures the essence of the object. So down below, we see this sketch of a cat from one of those books, right, that teach kids how to draw animals by drawing simpler shapes and then connecting them with connecting strokes. So let's let one more person in. Okay, great. So that's a sketch. And people have been using paper sketches forever. Many big ideas were initially born on a cocktail napkin, right, as people were sketching them. The nice thing about sketches is that although they may be rough and sort of unfinished, but they're very easy to draw, very easy to discard. And because of that, and because they convey the idea so well, I would argue that they encourage creativity. So we want to take advantage of that. Now, and for us, like I said, for today's talk, I'll briefly talk about several interfaces for sketch-based 3D modeling. So there's the need to create 3D shapes, and there's this need for professionals, of course, such as artists, architects, designers, but they typically use some of the existing professional software, for example, like Maya, right, for 3D shapes. And this is what you can use to create, for example, characters for a Pixar movie. Now, they allow you to create models that are very fine and precise, but there is a problem. This software, those types of software take a long time to learn. The learning curve is actually pretty steep for something like Maya or AutoCAD, right? And those models take a long time to create. So even professionals, even experts take hours or even days to create a model. But of course, they are important. They are heavily used in industry, and that's all great. But if we want to allow non-expert users to just sketch something quickly and easily, those systems are not suitable, right? So we want, like, take a person like me, right, who doesn't really know Maya or isn't particularly good in drawing, but I should be able to just quickly sketch something, just like I would sketch it maybe on a paper napkin. And the applications here could be for something like communication. So maybe I can just draw something quick on the iPad just by drawing maybe the outline of a particular shape. And then let's say the system creates a three-dimensional shape, and I can rotate it and use it to explain my idea to somebody I'm talking to. And the second application, I guess, would be video games. Yes, there are those characters that are created by professionals that look very fancy, like this yellow guy on the left-hand side. But then there's a potential use of, basically it would be really useful, I think, to allow kids to create their own characters if it's something they can sketch in just a few seconds or minutes without any preparation, without learning the software. So then they create something that looks very rough and simple, like this little cat on the right-hand side, but they, they might be really excited to be able to create their own character. And finally, we can use those sort of rough, pretty shapes that non-expert users can create when we search for 3D models in repositories that contain 3D models. So for example, Princeton has this shape retrieval system. And what they allow users to do, they allow users to sketch the shape roughly. So they'll create rough 3D shape using some of the previous work, not from Princeton, but they're using existing work from Japan on that. And then once the user has that rough shape, for example, here it's meant to be a plane. If you guys looking on the left-hand side and trying to figure out what that is, this is meant to be a plane. So then you can use this 3D shape to search the database for 3D models of real planes, both toy planes and real planes, depending on what you need. So maybe that would be another application. Okay, so now again, compared to those software, this different software that I described, professional software, the sketch-based interfaces, they allow users to create models that are informal, rough, approximate, but they can be created by non-experts very, very quickly and easily. You don't need to spend hours learning this software. You can just start drawing the way you would draw on paper. So that's the idea. And again, they used in different circumstances. You wouldn't use it to create a character for a Pixar movie. You use it in different applications. Well, I guess they could be used, the models that you can produce with sketch-based modeling, they could be used in the initial stages of design, when you're just thinking about stuff and just coming up with ideas, and you want to create something quickly, throw it away, and then move on to the next model. And once you approximately have what you want, then you can maybe go and create it more carefully and create a more detailed model in Maya. Okay, so hopefully the motivation for sketch-based modeling, for using sketch-based modeling interfaces is clear. And what we want essentially, right, is we want to do more than what we could do just by drawing on a napkin, right? So here we want to combine things that the user can do, which is sketch, with essentially what computer can do well, and let's say maybe infer 3D shapes from contour drawings. All right, so one thing to keep in mind as we talk about sketch-based interfaces today is that any sketch, and whenever we go from a 2D sketch to a 3D shape, this problem is under constraint, right? It's inherently ambiguous. So when we look, for example, at the circle, we don't really know if it's a contour of just a flat circle in space, or if it's contour of a sphere, or if it's contour of some kind of pancake or potato chip, right? So we don't know what the shape really is. So we have to just make a guess, and we need to come up with something which is likely, and maybe we'll want to restrict our surfaces to certain category of surfaces to make it easier, right? So if we say it has to be smooth shape without boundary, then suddenly this potato chip, right, pancake, circle, they don't apply. So it has to be something smooth without boundary. So on the other hand, if we say, okay, the sketch is meant to represent something which has planar faces, something rectilinear, like furniture. Well, then again, that gives us a hint and helps us infer 3D shape. That makes sense. But ultimately, it's never guaranteed, right? That based on the 2D sketch, we recover exactly the shape that the user wanted. We just need to give something reasonable, and maybe allow the user to later edit it, maybe from a different point of view. That's not something that's done in any of the current systems that I'm in any of the systems that I'm presenting today, but there's definitely work that allows users to edit shape from different points of view. All right, so that's regarding ambiguity of Sketch. And many, even when you talk about modeling, sketch-based modeling interfaces, there are actually many different kinds of those interfaces. So people worked on sketching three-dimensional curves. For example, there's interesting work on sketching a shadow of a curve in addition to the curve itself to create a three-dimensional curve. People worked on sketching rectilinear objects, again, like furniture. An example is shown on the right-hand side. So rectilinear shapes, right? The shapes such that the faces are planar. Let me add one more person. Okay. And people worked on sketching shapes that are more free-form, and I'll define roughly what free-form is in a few minutes. And then finally, have been lots of work in sketch-based interfaces that are much more specialized. For example, they focus entirely on sketching flowers. I'm just sketching cloves. If you focus on a particular sort of domain, then it's a little easier to infer shapes, right? Because you know that the user is drawing, for example, a piece of clothing. You don't need to guess from just general category, all the kind of different categories of shapes. You know, it's probably clothing, right? And then you can make some educated guesses about what it might look like given the contour. All right. So first, I'm just going to briefly talk about one particular sketch-based system that focuses on creating rectilinear kind of shapes. So the results are shown to you on the right-hand side. You can see you can create furniture, and then all of those 3D models were created with sketches, with gestures. So this work was done at Brown University, and it was done by Bob Železnik and his team. So this is not my work, but this is the work that influenced this whole field of sketch-based modeling interfaces significantly. And what these guys did is they said, well, we can come up with a set of gestures that could be used to create three-dimensional shapes of different kinds of shapes. So for example, when the user draws three line segments that intersect at 120 degrees, so we decided, okay, this gesture means that the user wants to create a cube. And the line segments, their length, right, will be width, height, and length of each side. Okay, or maybe when they draw a little circle, right, and then they draw another stroke that is attached to the circle, the way that's interpreted is that, okay, the circle is the cross section, okay, and then this other stroke, that second stroke that we drew, that it has to be in the it has to be perpendicular to the circle, okay, and then the circle should be sort of swept along this particular second stroke to create a generalized cylinder. So that's what this guy said. And of course, they needed to think of what's sort of the right, what's the correct gesture to use for different primitive, like cube, right, sphere, and cone, and so on. So what makes sense? What captures, I guess, important visual features of each shape? And I think they've done a great job. They came up with gestures that are very intuitive. So often they do stuff that's axis aligned, just because this particular paper focused on rectilinear shapes. So I just wanted to show you some of the other gestures they used, which I think pretty awesome. So for example, for a cylinder, just a regular cylinder, not a generalized cylinder, the user can just draw two lines that are nearly parallel. They won't be perfectly parallel because the user is just sketching. So as long as they're nearly parallel, you can just say, and there's a little circle that you draw at the bottom, it means create a cylinder. And I guess the width, right? So the radius could be determined from the space between the lines, And similarly, the length of the lines can correspond to the height of the cylinder. So there's a nice gesture for drawing a cone. For the sphere, I guess it's pretty self-explanatory. It's just a circle and a little circle in between, in the middle. So these are some of the gestures they used. And it means that sometimes the user will create the shape from one sketch, sometimes actually from two sketches. And they also allow the user to manipulate, to transform those shapes with sketch-based interfaces, but that's not something that I'm going to mention today. So that it gets more complicated. But that's a very influential paper. After any paper like this, there'll be usually multiple other papers that try to improve this work and create maybe additional gestures. So this paper was cited a lot in this particular field. So that's rectilinear shapes. Many more systems exist that try to do it in various ways, but we looked at one of them. So now we're gonna focus for the rest of the talk on sketching 3D free-form shapes, free-form objects. So what do I mean by free-form? The definition that's given is typically informal, but essentially the surfaces that don't belong to some other categories, they're not planar, right? So they're not rectilinear shapes, and they're not quadric. So for example, it's not like they're cylinders or cones, right? They're mostly smooth. So the normal would mostly change, the normal of the surface of this freeform shape will mostly change smoothly, except for maybe a few edges, corners, and so on. In the examples from real life could be things like, I don't know, sculptures, planes, animals, toys, terrain maps, right? So it depends. So those are the shapes that we'll be talking about. So how can we create a sketch-based interface that allows users to very quickly create them? All right, so I'm going to talk about three such systems. One is called TEDdy, then one that's called constructive drawing in 3D, and then finally, if there's time, we'll talk about smooth sketch. Let's talk about TEDdy again. This was a huge deal when it came out. It was the paper that cited a lot in this area because it came up with a very simple, but I think brilliant idea. We'd say, well, just allow user to draw a contour like the one shown on the left. This is contour of a snail. And then Takeo Igarashi's system would create a three-dimensional mesh, a 3D shape that matched this contour. And the user could rotate it, look at it, and then add some additional details by drawing on top of this one, on top of this shape. So I think what I'm gonna do is I'm gonna just show you the video of TEDdy, and then we'll very briefly at a high level talk about how some of those may be implemented. Okay, so let me just switch to the video. Just bear with me. Okay, here you go. I hope you folks can see. Hope you folks can see the video. Can somebody confirm that you're able to see the screen with the video? Okay. Awesome. Patrick says he can.
Yep. It's good.
Okay, that's great. So let's play it.
TEDdy is a sketching interface for designing freeform models, such as stuffed animals. The user draws 2D freeform strokes interactively, and the system constructs a 3D shape automatically. This demonstration is running as a Java applet on a standard PC. I will introduce the modeling operations one by one. When you draw a closed stroke on the blank canvas, the system constructs a 3D model by inflating the closed region. The algorithm is designed for the construction of round models, and it creates various naturally looking shapes. This is a snake. Our algorithm makes wide area fat and narrow area thin. This is a dinosaur. This kind of modeling required many operations in previous systems. This is a snail. We use real-time pen and ink rendering to encourage creative exploration. You can draw lines on the object surface by drawing a stroke within the object. Camera position changes when you hold a button on the stylus. Scribbling gesture on top of a surface line erases it. Extrusion is a two-stroke operation. You first draw a closed stroke on the surface, and then draw an extruding stroke. This is basically a sweep operation. With it, you can create various shapes, like this long extrusion. This is useful to create an arm or a leg. Or this fat extrusion. This is useful to create a head. And this thin, plate-like extrusion. This is useful to create a wing or a fin. You can also dig a hole using the same operation. The resulting model is always topologically equivalent to a sphere.
All right, so I'm gonna stop the video here. It just goes on and on and on. There's some other operations you can do, but hopefully you got the idea of how this system works. Just to clarify, they're using this style, the rendering style, the way the shape is rendered is called pen and ink illustration. So they're just trying to mimic the sketch of an artist. So it's deliberate. They could have displayed this three-dimensional mesh in any way they wanted, but that's how they chose to do it. To make it similar to a sketch. So in the operations that they have is inflation. So again, you'll hear the word inflation several times today. What we mean by that is going from an outline of a shape from the contour to the 3D shape that actually matches this contour. So he also has painting, extrusion, right? That's when you draw two strokes. Remember, first a stroke that's closed, let's say like a circle, right? And then you rotate the shape, and then once you're in a different plane, once you're perpendicular to this extrusion stroke, then you can draw another stroke, right? And it would essentially take, in this case, the circle, right? And it will just sweep it along the other stroke to create a three-dimensional shape. So cutting, erasing, I don't know if we've seen that one, but yeah, you can also scribble on the stroke that you drew to erase it. There's smoothing and some other operations as well. Now, the representation of a 3D model that's used here is a triangular mesh. So it's a polygonal representation. So that's how the 3D shapes are often represented. So as polygonal models. So that's what Takeo Igarashi is using in this paper. In terms of inflation, so he's using something called constrained Delanoid triangulation. And the goal here is to just take points. So as the user draws the outline, he samples the stroke. So it creates a bunch of points, right? And I guess we want to make sure they're as evenly spaced as possible. So typically there's some pre-processing. And then he runs one of the existing geometry algorithms that is able to fill this area with triangles. Okay, so we won't go into the details of how to compute Delanoid triangulation, but that's what he does, and it's a variation of Delanoid triangulation that is constrained. So we want our points on the boundary to be vertices of the triangles. As you can see, all of those points on the boundary are actually vertices of triangles. So it's not classic Delanoid, it's a variation of Delanoid, but the idea is to just fill it with triangles. Okay, so once we have it, we can slightly modify it. We can change the triangles a little bit. So we want to create so-called fan triangles. Again, I know I'm hand waving, so I'm not going into details, but that's what he's trying to do. And then that's an important step. Takeo Igarashi creates a sort of like a skeleton, a spine of this two-dimensional shape, which is a two-dimensional shape that we created from the outline of the shape. So he has an algorithm for creating such skeleton. And once he has that, this is how the inflation is happening in TEDdy. So imagine you have this 2D shape, right? Flat shape that you created from the outline that the user sketched. And you have that skeleton in there that you computed. So imagine you just sort of put it flat on the table. Well, of course, we are talking about things that are happening in the computer, right? But just for a second, imagine that we're putting it flat. And then we are taking that skeleton and we're raising it slightly. How much to raise will affect the thickness of the shape. And then what Takeo does is that he determines how much to raise that skeleton perpendicular to the surface. Sorry, how much to lift that skeleton along the normal to the surface of a drawing. So how much to lift it is decided depending on how fat or thin the shape is. So it depends on the distance from that skeleton to the boundary. Okay, so that distance is computed from the distance from this particular point in the skeleton that we're looking at to the boundary. And then once we lifted that skeleton up, we can connect it to the points on the boundary using those arcs. So we don't want to create, we don't want to use straight lines, right? Because otherwise the shape will have this sort of rectilinear kind of look. It won't look good, it won't be smooth. So he uses arcs. And then each of those arcs is filled with triangles again, like shown in the last diagram here. So if we do that for all the points on the skeleton, then essentially we have half of the shape. Notice that this is not the full shape, right? That's just half of the shape. And we have a three-dimensional mesh for that. All we need to do is repeat the same process on the other side of the shape, right? So exact same thing. And then we'll have a mesh that we can render. For extrusion, you need to do a bit more, right? We need to allow user to draw first this closed stroke, like in this case, it's a circle. Then if you remember, the user would rotate the view, we'll change the view, draw another stroke. And then what essentially we need to do is we need to take that circle and sweep it along that second stroke that the user drew. They are perpendicular to each other. So the second stroke is along the normal of the circle that the user drew. So we'll just sweep it along the projected stroke. And then what we can do is essentially we can just connect all those consecutive circles with triangles to create a 3D mesh. So that's how he does extrusion. Again, I'm giving you a very rough idea. We don't go into too many details. So I'm gonna now talk about painting. So for the painting, all we need to do is when the user draws a stroke, we need to essentially cast a ray from the camera through the points of the stroke that the user just sketched and see where this ray intersects our three-dimensional shape. So at that point, you already have a three-dimensional shape. And if it does intersect, well, I guess if it does not intersect the shape, then you don't need to do anything, you're done. But if it does intersect the shape, then you can just project that point on the three-dimensional shape. So you can compute its three-dimensional coordinate. And then you can do it for all the points of the painted stroke and just draw that line segment in different color. And because we projected it on the shape, it will look, it will appear as if it's right on the shape. Okay, so that's painting. And this is some of the results from the TEDdy system. So he used it in, I think in some preschools, he allowed kids to play with it. They were able to create animals like this quickly. I think he also has a game, a very simple game. And then again, kids could create their own characters for the game, which was attractive to many people. So, and it's their own character now that's fighting as opposed to some predefined model. Very influential paper, although the shapes have this rough look that's typical for sketch-based interfaces. Again, the goal is not to create characters that you see in Pixar. The idea is to create shapes that are approximate, but create them in minutes or seconds. So that was Teddy. And I just wanted to mention that that search engine that I mentioned earlier from Princeton that allows the user to search for many three-dimensional models. They have different interfaces for the user. So the user can actually sketch the shape from different points of view, like shown on the left-hand side. And in this case, they're just 2D sketches. That's what they initially did. And then once Teddy came out, they said, okay, let's have another option for the user. So let's allow user to use Teddy to sketch a three-dimensional shape, like this little plane I mentioned earlier. And then we can use this rough approximate 3D shape to search in the database of real life shapes. Like in this case, this toy plane that we sketched in seconds in Teddy, and maybe in a minute in Teddy, will be used to search for planes in a database. So that's one of the application areas for something like that. All right, let's see. So now I'll briefly talk about a different system. So that one is something I've done during my master's. That's a few years ago, as you can imagine. And it's called constructive drawing in 3D. And it definitely does build on Teddy, but it uses very different representation, and it allows us to create a hierarchy of shapes. Well, essentially what it's trying to do, it's trying to mimic those types of books that we have that teach kids how to draw animals by composing them out of simple primitives, such as circles, ovals, squares. You've probably seen those step-by-step instructions since you were a kid. So those are very common. And then once you create this hierarchy of circles, rectangles, ovals, and so on, in order to create a final shape, which is more detailed, you use connecting strokes. So you'll smooth them using those connecting strokes. And then you delete those basic shapes like circles and squares and ovals and so on. So that is the idea. So several ideas that we'll be using from the book in the system. We want to use rough sketching and refinement. We want to use those basic shapes. Here they were two-dimensional, but for us they'll be blobs. They'll be three-dimensional. We want to use those connecting strokes as well that the user can sketch. And again, we'll arrange the shape in a hierarchy, and we should be able to place different blobs in relation to other blobs. So I think what I wanted to point out is that although the result, like when you look at the inflation, the result will be similar to the system we just saw, just called Teddy, the algorithms are completely different. And here we're using implicit surfaces, something I'm gonna very briefly talk in a few slides about. So instead of maybe talking about all those operations using slides, I think I can just show you the video, guys. And then I'll talk about the surface representation. So let's look at maybe just part of the video. All right, so let me start the video. Yeah, so it's the student who worked with me, another graduate student who recorded the video.
We start by showing off the basic operations. The first is inflation. When the user draws a stroke, the system creates a blob that matches the stroke. We can turn it around and look at it from other points of view. Inflation can handle quite general stroke shapes. The thickness of the inflated object depends on the stroke. Objects can be rotated with a virtual sphere rotation or translated parallel to the screen by click and drag anywhere except the blob, or in depth by dragging on the shadow. The second class of operations has to do with the modeling hierarchy. Each object drawn is inserted into a hierarchy. Here the leg is attached to the body, which flashes yellow momentarily. As you see here, we can rotate a child blob about its attachment point, or drag that attachment point along the parent blob. We now draw a second leg, and then invoke the symmetrize operation. This creates symmetrical copies of child hierarchies, reflected in the plane of symmetry of the parent. Here we create a couple of hierarchies with these operations. The user can also paint on the surface of a blob. We use this to draw the pig's face. The third operation is modification. The user can make small modifications to the shape of the blob by drawing a stroke near the blob's silhouette. This removes some of the constraints that define the implicit representation, but adds others. The surface adjusts itself to meet the new constraints. You can use the same technique to make an indentation in a blob, as shown here. The stroke dips into the surface, and the blob adjusts its shape. The fourth operation is merging, in which pairs of blobs are joined into a single, larger blob. In the first form, automatic merging, the user selects a pair of blobs. Constraint points from the first that lie within or nearly within the second are removed, as are constraints for the second that lie within the first. The remaining constraint points are used to generate a new surface. Details of the blending algorithm are given in the paper. In the second example, a cross shape, the two again blend nicely. In the second form, merging with guidance strokes, the user not only selects the pair of blobs to merge, but also draws a stroke that indicates the shape of the resulting merge near the intersection. The result is a new blob that follows the guidance stroke. Here we see the same thing with another example. The guidance stroke smoothly fillets between the blobs, some constraints are removed, and the new constraints are added. Finally, we demonstrate animal drawing using many of the basic operations described earlier. First, a simple dog. We begin by drawing a body and a head, and merge them with the guidance stroke. Then we add legs, ears, and a tail, and merge them one by one into a final model. We elide several of the intermediate merge operations and show the final model. Next, we create a more complex animal, a camel. The humps are created with modification strokes. Then, the neck is drawn, as well as the head. Symmetrize is used to avoid redrawing the complex legs on the other side of the body. We conclude with some complicated animal models drawn using our system. Each animal took several minutes to draw. A kangaroo, a monkey, a giraffe.
All right, so that was the video. And I just wanted to briefly talk about surface representation that we used. So generally, whenever we talk about sketch-based modeling interface, there are two pieces for people to think about, right? There's an interface, and oftentimes it's gestural. And there's actually this question about what representation will you use for a surface. And generally, there are three different choices you can make. You can use polygonal representation. So this is what Takeo Garashi used in TEDI, the system we saw previously. So they used triangles, a triangle mesh to represent a 3D shape. We could use a parametric representation. So for example, those equations define a sphere actually. And S, I believe, is a latitude and T is a co-latitude. So for each ST, we can compute X, Y, and Z for the sphere. And then third representation, type of representation would be implicit. So we're saying, okay, there's a function that depends on X, Y, Z. So for example, it's X squared plus Y squared plus Z squared. And then it's level set. So the set of points where this function is equal to a particular value, for example, 1, this is our shape. So this is also a definition of a sphere. Right? This is a set of points where the function X squared plus Y squared plus Z squared equals 1. So that's yet another way. And then in this paper that we're discussing, we use implicit representation, not polygonal. So eventually, of course, when you render it, you will switch to polygonal representation, but for inflation, we use implicit representation. In particular, we use something called variational implicit functions. I'm not gonna go into details of it, but this, the problem that we're trying to solve is we have some constraints. You saw some of them in the video. So some of those are the points from the contour the user drew, some of them some other points that we create. And we want, what we're telling this function is we want that function to pass, we want the level set of that actually 4-dimensional function, the level set, which is 3D, to pass through those constraints. That's the idea. So if we look at it in 2D, for us, it's 3D, but if we look at it at 2D, it's a little simpler. So imagine that we have those little yellow circles, and we say, okay, for those points, we want the function to pass through them. Okay, and then there are these points that are slightly displaced along the normal to the contour. I show them by pluses, little green points, little pluses. So those constraints are different kinds of constraints. They just say, so at those points, the function should be positive. Okay, so similarly, we could add other points by shifting those yellow circles slightly along the normal outside, and we can say, okay, at those points, we want the function to be negative. Okay, and then we can come up with, once we compute the function, we can come up, in this case, with a line, right, that passes through yellow points, and that's our solution. So in 3D, we'll have 2-dimensional constraints, but also 3-dimensional constraints, as explained here. So the 2-dimensional constraints come from the drawing of the user. So when the user draws a circle, for example, we'll sample that stroke, and those points will be our constraints. We want the function to, want our surface to pass through them. Then we'll also, just like I showed you in 2D case, we'll also take a little, all those points on the boundary and then slightly move them outside the normal outside of the contour and say, okay, here the function should be negative. Okay, and then we'll also pick the center of mass of a drawing, and we'll take those, take this point and then move it outside of the drawing, so perpendicular to the drawing, as shown in that second diagram. So we'll, in fact, create two such constraints, right? We'll take the center of mass, we'll pull it out in front of the drawing and behind the drawing. By how much? That will define the thickness of a shape. So we can have something that's set, it's something just like a constant, or we can make it dependent on the distance from the center of mass to the boundary. So then thin shapes will be not fat, right? And then shapes that are wider, shapes that whose outline is wider will be fatter. So we could do something like that. So, but once we add those constraints, we can compute an implicit function that's supposed to pass through some of those constraints and be negative or positive at some other points, additional points that we created and that are shown by pluses. And then we can take its level set. Basically, we can just see where is this function 0? Where, what are the points where it's equal to 0? And those points will correspond to our surface, the one that we want. And we can just go ahead and triangulate it and render it to the user. I know I'm hand waving. There's no time to go into the detail of all of those algorithms. So it's very high level, but hopefully it will give you at least some ideas of how such problems are approached in this particular field of sketch-based modeling interfaces. Okay, and then let's see how we're doing on time. John, do we have a couple more minutes? I just wanted to maybe, there won't be time to discuss MoveSketch, but I just want to maybe show what problem it solves and then just show maybe the results, that's all. Would that be time?
Yeah, we have the full hour.
Okay,
full hour, so feel free to keep going. Yeah.
Wonderful. Well, we need to leave time for questions, so I'll be brief with the third system called MoveSketch. So again, just remind you that we're using contour drawings because this is something that people are fairly good at drawing, right? And they convey shape pretty well. Now, when you looked at the previous systems, you notice that their contours, right, looked pretty simple. They are very different from what you just saw in the previous slide, because those are the kind of contours you see in drawings, right? They're much more complex. So the previous systems were just not able to deal with them, and actually nobody currently can. So, but what we can do is we can take a step closer to that goal of taking this sort of a dog, like that yellow dog that the user sketched, and going to 3D shape. That is still too hard. There's too much ambiguity in the sketch, but we can take one step forward in that direction, so to speak. So we can start with a sketch like the one shown on the bottom and create a 3D model that matches it. And you can see that sketch on the left-hand side, unlike sketches in the previous systems that we saw, has various junctions. So we are interested in contours that are more complex, that contain those junctions that you can see here. And in particular, they contain something called T-junctions and cusps. So if you guys look at this T-junction, right, it's called T-junction because it looks like letter T. And then if it looks like a T-junction in 2D, essentially in 3D, it corresponds to two surfaces that are overlapping. So when they overlap, their contours also overlap and create this letter T. And cusp is a little bit more complex. You can see this is when a surface sort of folds onto itself, right? And then when you look at the contour in 2D, it looks like this cusp. So we want to be able to handle contours that look that way. We need to make some other assumptions. We're dealing specifically with shapes that have no boundary, that they're smooth and closed, like I said, without boundary, right? But we need to make sure that the view is generic and not accidental. There's some other assumptions about how the user actually draws those contours. But if we make that assumption, we can actually create 3D shapes from such contours, from a subset of such contours by following the following algorithm. Again, I'm gonna be very, very high level here. So the way this works is we start with a contour that the user draws, then we find hidden contours. As you can see, the user was not able to draw all the contours. Right? Some contours need to be inferred. And in that second image, the one that that's shown in the red square, in the red rectangle, sorry, the hidden contours are shown in green. I guess it's green or blue-green. Okay, and then we can assign depth, relative depth to different parts of the contour. Okay, so let's say the contour that the user drew is at level 0, right? And then some of those contours will be at depth 1 or 2. So there's an algorithm that we have that does it. And then we can cut the drawing into pieces. Okay, in this case, we'll get a little So triangle-like shape, and then this shape of a blob, sorry, not a blob, a bean, right? It's like a big bean. It's shape of a bean without this little triangle, and then we create different copies of those. Again, the algorithm will tell us how many copies of each to create, and then we can stitch them. We can sort of pretend that we're just stitching them along the boundary in a certain way. And in fact, in a way that gives us a topological representation of the shape. So it will be flat, but it has the right topology. And all we need to do is inflate it. And then we create an actual three-dimensional shape. So that's the idea. And if we use it, this is the sort of results we can get. Notice that the legs here appear only on one side of the body because this is a general system. We don't know that we're drawing animals. We don't know anything. This is purely mathematical. And in this case, we don't know if the user is actually drawing a dog, right? And it's just uses information from the sketch. All it can say and from the sketch is that, okay, given how the legs were drawn, it looks like they are in front of the body. In this case, unlike the previous system, we don't need to draw the legs separately. We infer them from the sketch once. The user didn't have to give any additional input. So just purely based on those junctions, right? T-junctions and cusps, that we're able to infer that the legs should be in front of the body. And we don't, of course, know that they're actually legs. So we can then deal with objects that have self-occlusion. So you can see that this worm, right? You can see that the head of the worm actually covers the tail. So part of the tail is hidden. But because we infer hidden contours, we're able to recover that and realize, aha, it is still part of this part of the surface. So I have a video for that, but I want to make sure we leave time for questions. I know it was very brief and very high level, but hopefully it gave you guys a glimpse into this fascinating field of sketch-based modeling interfaces. And let's use the remaining time for questions. Any questions?
So what is the next level of this? Are we adding more T points? Are we adding more contour? Are we like, what is?
Yeah, that's an excellent question. So where do you go from here, right? So, okay, so you can do that, right? But clearly we're still not at a place, let me just go here for a second. So, so we're not still at a place, right, when we can create this spot the dog, right? That yellow dog from this contour. So yeah, where next? Yeah, so what's needed is, so the issue we cannot reconstruct the spot the dog, and nobody can do it yet, is because there's too much ambiguity in the sketch, right? So we need to get better at guessing the hidden contours. We need to, I guess, allow the user to help resolve some of those ambiguities. So because once you recover the hidden contours, some of them will be incorrect, right? Because we just made our best guess. So the user should be able to go and say, okay, show me that intermediate step. That is not completely right. So let me maybe fix that. Or maybe we can, in fact, the smooth sketch system actually did have a suggestion engine. So it will, whenever there are different options, it will try to give the user several options and say, okay, pick the one that you meant. So just doing more of that would be the next step. But I think also maybe the next step would be using kind of machine learning here, right? We could just say, okay, let's
So
just have, yeah, yes, Marisa.
You train the algorithm. If you see this intersection, give this option to the user.
Yeah, I think we need to do it not just per intersection, but I think we could just have a bunch of drawings, right? And then corresponding 3D shapes. Creating such a database, of course, such training set will be difficult, but imagine that we had it. So then, yeah, maybe we can, maybe the system can learn how to make better choices. And then, of course, ultimately, we still don't know what the user meant and what the user wanted. So stronger suggestion engine that gives the user several options and allows the user to intervene interactively and fix something and change something. Because that's one thing we have, which we don't have on paper, right? The user can just always provide feedback to the system and adjust it. So I would say those are the next steps, but it is very complicated problem, right? It's like computer vision issue. But yeah, I mean, there's definitely something that can still be done.
Thank you.
Any other questions? So, and there's a lot of work in this area. So we just, again, scratch the surface. There are hundreds of papers. But yeah, this is the last one is, I guess, the Eurographics paper, the one with sketching animals, and this one, which is more general for sketching mathematical sort of surfaces and using and inferring shape from contours that contain junctions. This is something that I worked on when I was a PhD student. So yeah, I love this field. I'm not doing research in it currently, but I still do care about this particular domain. Okay, so let's see how we're doing in time. Any other questions?
I think it's fun if we continue just drawing about dogs and training the algorithm on just drawing on dogs with kids.
Right, but we want, I guess what we want is though more general. So I don't want to train it on animals specifically, right? So I want to be able to sketch anything. So I want the algorithm to be sort of mathematical, but yeah, I mean, it does make sense to train it on real three-dimensional shapes. Right?
Yeah, that one would be easier. Okay.
Yeah.
Anyway, this is very interesting to me. Thank you, Professor.
No problem. No problem. Any other question? All right. So I can show you just a bit of that video if you guys want. For the last system, yeah, so we can play it in the remaining minute. And if you think of any questions, just interrupt. Questions are more important than the video. Okay, so here we just again draw this shape of essentially like a kidney bean, right? And then you can see in the green, it shows you what the system inferred as hidden contours, something that the user did not draw. Okay, and this is where we assign depth to those contours. And this is where we create the cutouts, right? This different the pieces from the contours, and then we'll need to create different copies of each of those pieces. Now that when we rotate, you can see that it created 4 copies of this little triangle and then 2 copies of this green part without the triangle. So now we can stitch them along the edges. We just need to be careful how we do that so that topologically we have something that it's equivalent to the bean. Okay, so the edges that are shown in the same color will be stitched together. So they'll be connected together. So we'll build a 3-dimensional mesh that connects those edges. And so that's what it would look like if we just stitch contours. And then if we fill it with a mesh, it will give us something that, of course, is not nice and round and smooth, but it will give us something that topologically is correct. So this is if we just fill that contour. You see it looks pretty ugly, but topology, it has the right topology. So all we need to do now is inflate it, just make it smooth. And we can do it by minimizing the overall curvature of the shape. And then we can actually get a 3-dimensional shape that matches this contour. So notice there's no assumption that the system makes about what you're drawing. It's purely mathematical approach. It does not know that you're trying to draw like the body of the dog with a leg. It has no clue. Again, in green, it showed you hidden contours. Different colors here correspond to different shapes, to the shapes that the contours split the drawing into. Again, our algorithm will create different number of copies of each of those pieces. It will glue them. So we have the right topology, then we'll create a 3-dimensional mesh from that, very rough one. Again, just give us the right topology. But the interesting part is that, see, the system guessed, right? That based on the T-junctions and cusps, it guessed that the part that is meant to represent the leg was actually in front of the body. It did it without knowing that you're drawing a leg, just purely based on the contour. So here we're drawing a worm. Remember I mentioned that part of it is hidden, but because we are doing hidden contour completion, it will be able to realize that, okay, this is part of that tail. And if you're wondering how it was able to figure it out, it's just based on the orientation of contours near those junctions. And it's able actually to provide suggestions also on if the hidden contours were guessed incorrectly, it provides alternative options, because for any drawing that contains T's and cusps, there are many actually possible hidden contours typically that you can guess. This is, I guess, like a cloud shape type of, with many, I guess, cusps and T junctions. Right. So there's still a lot of work remaining. As you can see, we're still nowhere close to doing spot the dog, but at least it's a step in that direction. At least the contours here could have junctions. That's the biggest, I guess, difference compared to some of the previous approaches. It's like impossible triangle, but of course, if you look at the rectilinear shapes, that would be impossible, right? But in the shape, in the domain of 2D shapes, so in the domain of smooth shapes, this is actually a normal sort of possible shape, not impossible. All right, folks, any other questions? Well, thank you so much for attending. If you think of anything, you can always email me and I'd be happy to answer your questions. Good to see you all.
Thank you so much, Dr. Karpenko. We appreciate the presentation.
Thank you, John.
And if folks have any, yeah, of course. And if folks have any questions, they can definitely reach out to Professor Karpenko. Just wanted to give everyone a reminder that next week we will be having Professor Vahab talking about computer network and security. So that will be our next presentation. I appreciate everyone joining us this morning and look forward to seeing you all soon.
Bye, guys.
Have a wonderful day.
Thank you.
Thank you.
Take care. Bye.